So let's finish up section 8.2. Power series within their radius of convergence can be differentiated term by term and integrated term by term. What that means is that if we have a power series like this right here, and we want to take the derivative, we can just bring the n down and subtract 1 from the exponent. Just a typical derivative. So that's what I've done right here. However, if you look at that power series, when n is 0, I get 0 for the first term. So what we're going to do is just start at 1. So when we take the derivative, we're going to start right here, n equals 1 to infinity, n cn x to the n minus 1. And then when we take the derivative again, we bring that n minus 1 down. That's what you see here, and subtract another 1 from the exponent. But once again, when n is 0 and when n is 1, these two terms vanish, so let's just start with n equals 2 and go to infinity and use this expression here. All right, so let's do some examples. Find a power series expansion for g prime and g. So g prime of x is, I bring the n down. Well, I'm going to start at 1, n equals 1 to infinity. I bring the n down and I get n cubed c sub n, and then x to the n minus 1. And then for g double prime, I'm going to start at 2, bring the n minus 1 down, so I'll have n cubed times n minus 1 cn x to the n minus 2. All right, let's just do one more of these. G prime is the sum, n equal 1 to infinity. If I bring an n down, n over n factorial is 1 over n minus 1 factorial. So my new coefficient will be cn over n minus 1 factorial, x minus 1 to the n minus 1. Those same derivative rules hold if your power series is centered at 1, which this one is. All right, and g double prime, we're going to start at 2, and then when I bring an n minus 1 down, we get n minus 1 over n minus 1 factorial, which is 1 over n minus 2 factorial. So this will be cn over n minus 2 factorial, x minus 1 to the n minus 2. Okay, now let's take this a little further. I have an expression here, and I want to write it as a single power series in x to the n, and I'm going to assume that y is this power series here. So I always start with writing down my derivatives. So I've got y equals the sum, n equals 0 to infinity of cn x to the n. Y prime is going to be n equal 1 to infinity, n cn x to the n minus 1. And y double prime will start at 2 to infinity, n times n minus 1 cn x to the n minus 2. Okay, then I plug in. So I'm plugging in y double prime and y prime into this expression. All right, so I get 2, and then y double prime is the sum, n equals 2 to infinity of n minus 1 cn x to the n minus 2. And then I have plus 1 minus x, y prime, which is the sum, n equal 1 to infinity of n cn x to the n minus 1. Okay, now I'm going to distribute. So I'm going to distribute this 2, and I'm going to distribute this 1 and this negative x. So this expression right here is going to give me 2 power series. So I'll have the sum, n equal 2 to infinity of 2n minus 1 cn x to the n minus 2. And then I'll distribute the 1 first. I'll get the sum, n equals 1 to infinity of n cn x to the n minus 1. And then distribute the negative x. So minus the sum, n equals 1 to infinity of n cn, and if I multiply x to the n minus 1 times x, I get x to the n. All right, next step, I want to reindex. All right, this first guy, I need to add 2 everywhere in the formula. So for the first infinite series, I'm going to start at 0, and I'll have 2, n plus 2, n plus 1, cn plus 2, x to the n. The second power series, I'm going to have to add 1 everywhere in the formula. So that one will start at 0 also. And I'll have n plus 1, cn plus 1, x to the n. And the last one I don't have to reindex because it's already in x to the n. Okay, now I need to cull. And what I mean by that is before I can combine, they all have to start at 1. The first 2 power series don't start at 1. So I need to cull off the n equals 0 term from the first guy, which will give me 4c2. And then I can write the first guy, n equal 1 to infinity of 2n plus 2, n plus 1, cn plus 2, x to the n. And then from that second power series, I need to cull off the 0 term. And so that will give me C1 plus, now I can write down the rest of the power series, 1 to infinity, n plus 1, cn plus 1. You can see why I left a whole page for this, huh? X to the n, and then the last one I just leave alone. Okay, and my final step is to combine. So I'm going to put my constant terms out front. That's 4c2 plus c1. And then I'll have a single power series, which starts at 1. Big bracket. And I write down all my coefficients. 2, n plus 2, n plus 1, cn plus 2, plus n plus 1, cn plus 1 minus n cn. Close bracket, x to the n. And there it is. Okay, so I'm going to wind up with giving you a preview of what's to come, how to solve a differential equation using power series methods. And I've chosen a particularly easy differential equation to solve. And some of the steps are old, so I've written down most of the steps, and we'll just walk through those, and I'll show you what's new. So we're going to assume that y is power series sum n equals 0 to infinity of cn x to the n, and we want to find a power series solution. So step 1 is to take our derivatives. I did that. Nothing new there. Step 2, plug into the differential equation. So I plugged in y prime and y. Now what's new here is that this is equal to 0. On the previous page it was just an expression, now it's an equation. So step 3, I had to re-index this first guy, and I did that, and you can follow through and make sure I did that step correctly. And again, I have an equals 0, it's an equation. And then step 4, I had to combine, so I had a single power series. Now these both started at 0, so I didn't have to cull anything out. So this is step 4, and again, I have an equals 0. Okay, that's about as far as we got on the previous page. What's new is that since I have an equation, so this part all here, this is new. Since I have an equation set equal to 0, I can set each coefficient equal to 0. And in this case, these are my coefficients. So I set that whole expression equal to 0. And that's what I did here. And then we want to solve for cn plus 1. So this is what I get. That's called the recurrence relation. And that's valid for wherever the summation starts, which is n equals 0, ... Okay, now I can start computing those coefficients. When n is 0, literally put 0 in for n, and over here you get 5c0, which I have here. And then when n is 1, we're going to be able to write c2 in terms of c0, because c2 is 5 halves c1, using the formula up here. But I know c1 is 5c0. So now I know that c2 is 25 halves c0. And then when n is 2, I can write c3 in terms of c2, but then I can write c2 in terms of c0. So you can see how this goes. And that's why it's called a recurrence relation. And so now what I do is I plug all those in to the information I have. I'm assuming that y is this power series. This is just my generic formula for a power series centered at 0. But now I can replace those c's with what I know. So y equals c naught is just c naught. Don't know anything about that. But I do know c1 is 5c naught, and that's times x. And then c2 is 25 halves c naught, and that's x squared. And then finally, C3 is 125 over 6 C naught x cubed. And you're usually told when you're finding power series solutions how many terms you want. Otherwise, you could be here all day. All right, now let's factor out a C naught. So I have a constant, and then 1 plus 5x plus 25 halves x squared plus 125 over 6 x cubed plus ... Well, it turns out, LOL, this is nothing more than the power series expansion for e to the 5x. And I wrote that down in the box below. We could have solved this differential equation just by separation of variables, and we would have gotten y equals a constant times e to the 5x. Well, that's exactly what we're getting here. We're just getting the power series version of e to the 5x. Amazing. All right, so in the next section, we'll solve more differential equations using this method.